This is going to be a video on a 327 small journal 2-bolt main block build. Didn't do much videotaping, but you need to clean that block with a good high detergent and a pressure washer and some bristle brushes to get in all the oil passages and such, and just make sure that block is really good and clean before you start your build. You also want to look at the cam bearing placement as it comes back from the machine shop. There is a lot of controversy on what's the best placement, but use your best judgment and do your research.
Set the end gaps on first and second piston rings on each cylinder individually. As you can see, I've got the first top piston ring put in here, and what makes a great squaring tool is just to take your piston, push it in there just a little bit, nice and straight, and then that'll keep it straight in the bore so it's not coxing an accurate measurement. So for this bore, which is 4 inches and 40 thousandths, there's a minimum of 16 thousandths to 18 thousandths gap for the ring, and this gauge is a 16, and it is not sliding through, it's just going through just the very tip, barely, if that. So what I'm going to need to do is run this through a ring file and open it up to the necessary gap. So the thing to do here on a ring file is butt the rings up against these stops right here, squeeze the ring together, and turn the crank on the file so that you're filing towards the inside of the ring, away from the ring face. And then when you get your a little bit done, you can take something like a honing stone just to dress up the corners so you don't have any jagged edges, and recheck the ring gap in the bore again. Okay, I've got the 16 thousandths feeler gauge, and I've got the ring in the cylinder, and it's squared off with the piston as we talked about earlier. And I'm just gonna slide that in there. As you can see, it just seats in there and it's just firm, not tight, not loose. These rings just come loose in bags, so after you fit each ring, like this one I just did, it's good to go ahead and group that with the piston it's going to be going in for that bore. So I've got a box of pistons that have all nice individually packaged there, and I'll just put the ring set in with each piston as I go. Alright, we've got our little small block 327 with all the main journals in, and caps are torqued down to the specs of 80 foot-pound. What we're going to do is use a set of telescoping gauges, put those in the bore, check the diameter with this set of outside micrometers after using this telescoping gauge to check some bearing clearances. After we get our opening sizes, then we'll go back to the crankshaft, put the outside mic on it, and see if we're in tolerance. I got the first reading, and it looks like it's going to be 2.302 thousandths. So if the crank main journal is at 2.3, as it should be, it should end up having about 2 thousandths of an inch bearing clearance. Well, here is the crankshaft I'll be running. It's an Eagle Specialties 4340 crank. As you can see by the numbers, it's for 327, 3.250 stroke, and a 5.7 rod. This one is designed to handle way more horsepower than my little engine will ever extend to it. The only reason I got this crank is because it was very inexpensive in relationship to trying to find a original forged steel crank that was in great shape. This particular crank had the rod journals actually manufactured for 350 rods, which is a larger journal, and they were selling this cheap. It ended up at my doorstep for $385, so this is the route I went, and it actually made it less expensive when buying aftermarket connecting rods, since they are still 5.7 length but carry the larger journal as a 350 crank would. So I just got through measuring all the main journals on this crank, which I'm very impressed. They all ran exactly the same, which is just 1 thousandths underneath the 2.3 main journal size. I had
for the most part, 3/1000 clearance on almost all my rod bearings. I had one that was 2 9/10,000ths and one that was 2 8/10,000ths, which is all in, you know, good running order. And so we're going to move on to the rod bearings. Before I start checking bearing clearances, I thought I'd give you guys a quick look at these rods I'm running. They're a Scat 4340 rod, 5.7 length, and they are bushed for full floating pins. Unique thing I like about these from the stock rod is they got the alignment dowels, so they keep the perfect alignment with the rod when they're put back together. And they run some good ARP fasteners for rod bolts. Checking this first rod with the telescoping gauge and putting the micrometer, and it looks like it is 1.998 thousandths. After checking this first rod journal, it looks like we're at 2.1 inches exactly, so that should give me 2/1000 inch rod bearing clearance. So next, on to the other 7. On the rod bearings, you can see we had anywhere from 2/1000 to 2 2/10,000ths, which is pretty good bearing clearances, so we're going to run with that. Got all the main caps now torqued to 80 foot-pounds, and we're using ARP studs, of course using their assembly lube on the washers and threads of the nuts for the torque spec. Anyway, we're checking in play now, and what I'm going to got is the crank set all the way back and zeroed my dial indicator in. And I'm going to put some pressure on the back of the crank. It's kind of difficult to do this and hold the camera, but it looks like we have 4/1000ths in play. That's pretty good. Usually I know the specs from GM are pretty loose, from 3 to 11, and most typical performance engines it's going to be anywhere from 4 to 8, so we're good. So I brought all this inside the house by the grace of my lovely wife, so I can assemble the pistons to the rods, and I've got everything aligned out here. Got my clips, rods, pistons, piston pins, and what I went ahead and did, since I matched, of course, those file fit rings to each of these individual pistons, I just went ahead and put those back in the bags the pistons were in and labeled them and stuffed them right back in the box. So I'll make sure the right rings go on the right pistons with the right rods, which have been also checked for clearance with the crank in the positions that I checked on the crank. So everything should be good to go. I'm going to get ready started on the assembly. We say I have a set of Hyper-Eutetic Speed Pro pistons. They're 40/1000ths over. These are the ones that have the Teflon skirts on them. Just want to make mention, when you're doing the 2-valve relief pistons, it's important the orientation of the connecting rod. As you can see, there's a large radius on this side of the rod and not on this side. So it's important when you put the pins in the pistons and, that you mount them up with this facing the radius along the side of the crank journal. So this being number 1, number 2 is going to be directly across from it. So you want to hang the piston toward the orientation of this one has the large radius facing the other side. Those will be on the same journal. I wanted to make quick mention that the locks, you want to make sure they are deeply seated into the groove all the way, and that the open end is facing the bottom of the piston skirt. Things a little bit more streamlined. I like to go ahead and get all the clips put in one side of the piston. Go ahead and get some oil, motor oil. This is Cam's break-in oil that I'm going to be using anyway with the motor. And I go ahead and oil the bosses as well as the pin before it goes in, and also oil the rod bushing, and that way when everything slips together, get oil on plenty on everything. But just getting that first clip in there makes it a streamlined process as far as not having to get your hands cleaned off every single time to put the next wrist pin clip in. I'll go ahead and do is put all the oil and all the pins, get all the rods mounted up, and then come behind it after I'm done doing that and install the last of the clips in every rod pin.
So this is going to be the best representation I can show you of what I was talking about earlier without this actually being on the crank. See a large chamfer out, large chamfer out, and vice versa on down the line. And this would show you the representative of the front of the block being over here to the right. The number one piston is the furthest bank out. And so that would be the staggering of them with the large chamfer of the rods outward on each rod journal. Okay folks, we're getting ready to install this Comp Big Mother Thumper hydraulic flat tappet cam. As you can see, it's got 500 lift on the intake, 486 on the exhaust at 1:5 rocker ratio, and we have duration at 50 of 243 on intake, 257 exhaust with 107-degree lobe separation. And once I get it in, we'll set up everything to start the cam degree in process. I'll be using Comp Cam's Pro Cam and Lifter lubricant on all the journals and cam lobes as I install it, and we'll get a little shot of that just here in a second. Just wanted to make mention earlier, I didn't, but some of these camshafts, the core of them has a lot of casting, flashing that's off to the side of the lobes, and I went through the cam and pretty much got rid of all that just to prevent a possibility of that coming loose or later as the cam breaks in causing scraping on lifters and such. Just a little bit of detail, maybe overkill, but anyway, went ahead and did it. And go ahead and lube that distributor gear drive on the camshaft as well as the lobes and journals as you're getting ready to install the cam. Some of you may be buying a timing set that has these different keyways on the lower sprocket, which will advance or retard your timing, cam timing by 2 degrees. And most sets are going to come with instructions on lining that up depending on what you want to do. This one is going to be set straight up without advance or retard, and then checked with the cam degree in procedure, and we'll go from there. I'm getting ready to degree this cam in, and got the degree wheel bolted up and makeshift little pointer out of a coat hanger, and I've got a piston stop up here on top of the number one cylinder. So to find top dead center, you can start out anywhere on this wheel, rotate this clockwise till it hits the piston stop, and make a note of how many degrees that is, and then rotate the engine the opposite direction until it hits, and take a note on that position on the degree wheel. Count the total degrees difference and split that and recenter that on top dead center, and then when you're done you want to recheck it. Just run that through the same procedure again. Okay, getting ready to find top dead center on this engine, so we can go ahead and start on the cam degreeing. As you can see, I got a piston stop and it stopped shy of being top dead center. I've turned the motor clockwise until it's hit that stop and just hit the 0 right there. Then I'm going to spin the motor the opposite direction and see how many degrees it is from there, and split the difference and recenter the 0 for top dead center. It's been rotated counterclockwise now, and I'm at 44 degrees, so 22 degrees from this mark would be the top dead center mark for my degree wheel, which would be set at 0. After moving the pointer, or moving the degree wheel 22 degrees back to the pointer, rotating the engine around now is top dead center, as you can see. And from here on out, all this will be rotated clockwise in the direction the motor's running to make any variance in the time and chain show up in the direction of operation. Okay, with my dial indicator on the intake lobe, number one cylinder, I'm going to rotate the engine in the clockwise direction and get a mark on when it hits maximum lift. You can see right there it hit maximum lift. I'm going to have to back that off just a little bit. Go back in the clockwise position. Make sure to stop it right in there and zero out the dial indicator. Okay, now that that is zeroed out, what you can do is run the crankshaft counterclockwise in the opposite direction and get all the slack out of the valve train and go well under 50 thousandths before maximum lift. So that should be enough there. And I'm going to roll it back clockwise, and I'm going to stop right when it gets 50 thousandths of an inch before maximum lift. It's right there, and then I'm going to take a reading of the degree. We have our mark. It looks like 56 degrees before top dead center. I'm going to go ahead and rotate it back clockwise until we reach 50 thousandths on the other side of maximum lift, going clockwise with the motor. And I'll take another reading right there. I have a reading of 148 degrees before top dead center. So what I've done with those two readings of 148 and 56 is added those together at 204 degrees, and then you divide it by 2, which comes out to 102, and that is the intake center line of 102 degrees in which the cam is supposed to be installed. So we're dead on, good to go. I wanted to take a look at something real quick. This is the double roller set I pulled off this motor, and if you can see side by side the difference in the link design. Not only that, but the size of the rollers. This piece that I've got on it is a much heavier duty Cloy's double roller time and set. The other thing you'll notice is right here on this part of the chain that rides in the sprocket, these are fixed. They don't move. They're pressed in. These on this timing chain, if I can get a shot of it, let's see if I can turn it around this way. These are what you call a true roller, where these will spin, and I'm not getting a very good shot of that just because it's camera, but anyway, this is a true roller timing chain. I wanted to take a step back and just pull the cam sprocket back off real quick to show something that I've modified. Is instead of having the pressed in plugs in the front of the oil channels through the lifter valley in the block, I went ahead and tapped those with a pipe thread, a 1/4 inch pipe tap. It's important not to go too deep. It's a very light cut in the block with the threads. You don't want to have it where the plug is going in and blocking the oil channel, and that makes it a little bit more secure than just the press in plugs. I like to do the wipe down of the cylinder walls one last time before I put motor oil in them and putting the pistons in. So just spray some WD-40 on a paper towel, get in the cylinders really good, running this way and long ways, and then after you're done, do a little inspection and see if you see just a little bit of grime. Go ahead and give it another wipe down. You want to make sure those are really clean and good to go. I did wash this block with high pressure soap and water before this, but you can see that stuff that really gets embedded during the machining process, and you want to get all that out of there. I'm using this new ring compressor. I've not used one of these tapered ones before. I've always used compressor spring compressed type ones before, the band type.
And this one is a lot easier to use, although if you're going to be building a lot of different size bore engines, this would rack up a little bit of money in your investment for buying ones for different sizes. But I really do like take a little look at the ring orientation. I don't know if this camera's going to pick it up, but right in the center at the top of the Speed Pro symbol, you'll see that the oil ring where the gap is, those tangs are pointing up as to not catch the oil holes, and then the oil rings are spaced 180 degrees apart at the pin locations. And also the compression 1 and 2 I'm spacing at 180 degrees from each other, and putting those at the pin location just because of my theory being with the piston, any rock in the bore at all, that these would be on the side and not the front and, I should say, top and bottom side as you're looking at it in the bore. The gaps wouldn't be there where the most loading is. I'm going to go ahead and just get a little bit of motor oil on this number 3 journal just right before getting the rod clamped down and in place, and spread that out a little bit. Alright, with the cap screws ARP and coated with the threads coated with the ARP fastener compound lubricant, we're going to go ahead and get these torqued in at 45 foot-pounds. This is the first one I've built that had cap screws instead of rod bolts, so typically I would use a rod bolt stretch gauge to get the perfect yield on the fastener, but these are recommending just to torque in at 45 foot-pounds. These can be torqued in sequences, stepped up, just after having a lot of experience with this type of work. I just pull these up slightly on each side. I've got my setting already at 45 foot-pounds on the torque wrench, so I'm just going to draw these up slowly and evenly and until I hit my torque stud. And you heard that first click right there, and there we go. I've got all the rods and pistons in, and the side clearance between the rods came in between 11 thousandths and 13 thousandths throughout, so that's a good thing. And we're going to go ahead and get the oil pump intermediate shaft and the pump put on in the pickup, and from there probably get the keyway installed for the harmonic balancer, get the timing cover on it, and go ahead and put the oil pan on it. I'm going to be using this Melling 10555 oil pump, and it is a high volume, high pressure pump. It does come with optional springs. You can lower or raise the oil pressure in which it operates. One of the cool things, or a couple of cool things, is, for one, it uses a 3/4 inch intake instead of a 5/8 on the oil pickup. The other thing is it's actually a bolt-in pickup tube instead of having to press it in and weld it. And when you order one, you just give them your pan depth, and they send you the pickup tube. It's designed for that depth oil pan. The other thing, of course, is our ARP intermediate pump rod. Well, here was a bonus. I didn't realize this, but when I opened up the pump box, here was its own intermediate shaft, and it has a rib inside there, which I don't know if the ARP does or not, but they're saying to use this intermediate shaft and not a substitute. But that was pretty cool, and I can send the ARP piece back. But just a nice feature with this milling pump. I've got my oil pump and pickup tube all mounted up, and I set the Milledin 6-quart oil pan on top of it, and it didn't hit the oil pump pickup when it sat down on just a flat rail, the block without a gasket. What I'm going to do now is just use this piece of Play-Doh, put the pan on there, see what the distance is from the bottom of the pan to the pickup, and then also account for the gasket thickness to make sure I've got adequate clearance from the bottom of the pan, not too much, not too little. You know, just like with machine work or parts, aftermarket parts that you buy, you know, do like Ronald Reagan said, trust but verify. And pretty much this is what this whole process is just verifying what should be. So here was the impression left after putting the pan in. You can see it's pancake down there. I'm just going to take my dial indicator, my caliper, sorry, and run this down till it touches. Take a look here, and it looks like we're right at 200 thousandths. This is going to be under a 1/4 inch, and then of course I'm going to have to measure my pan gasket and see what that thickness is and see how much that'll set that off. I'm using a rubber one that has the metal sleeves in it, so that'll give me a good accurate indication of just how far that will compress, so I won't have to be guessing at, say, like I would with the cork gasket. After measuring this sleeve in the rubber gasket, compressing the rubber so I could get down to the actual metal, and taking a second impression with a little bit better gauge of what was going on without my camera being on, it came up with 385 thousandths. So that's just 10 thousandths over 3/8 of an inch clearance for the bottom of the pan to the bottom of the pickup tube. So that's a good clearance. We're good to go. Last but not least, on the bottom end button up, the oil pump bolt aftermarket fastener was torqued to 65 foot-pounds. Got the timing chain cover on and left it loose until I get the harmonic balance in there, just in case it makes for better seal alignment because of the line bore. We'll tighten that up after the balancer's in. Got my balancer installer in place and got all the threads lubed up with some fastener lubricant. This part always makes me a bit on the nervous side. Looks like I got about 2 thousandths interference between the crank size and the balancer size, so if this goes on a little rough, I'm going to have to pull this back out and have this machined and reduce those interference tolerances. Okay, I got the harmonic balancer on. It needed to be bored out 2 thousandths of an inch. There was too much interference for it to go on. So got that done. Got the degree wheel back on. Piston stops back on, and what we're going to do is just get this thing back on top dead center, and then take this Moroso adjustable pointer and get that even with the top dead center line, and that will be set up for good. Okay, I've got one head torqued on, installed and torqued down. These are using the ARP head studs, and we're using thread sealant on the studs that go into the coolant passage, and then using the ARP fastener assembly lube on all the washers and studs and nuts, and torquing those down evenly in 3 steps to 70 foot-pounds of torque. Over on this side, you can see I still have yet to do. What we're using here is a Felpro Permatorque SD, which is severe duty. These don't have the separate ring around the cylinder combustion chamber ring top or piston top. I've heard some complaints that people are having impressions left on their aluminum head, and I was talking to my machine shop that owns racing engines, and they said they use this gasket a lot and has been very successful in using it. So that's what we're going to use, and I'll get this next cylinder head on. Gasket's in place and we're ready to drop the cylinder head on it. I did not see anything that was marked top, but I did see this little symbol on this side of the gasket which shows a fastener on top of it, so we're going to imagine that this would be the top if it does matter at all. I couldn't find any literature technical support on that on Felpro's website. Okay, as you can see, I got the other cylinder head on, and I wanted to talk about a couple of things. One thing is torque patterns. I didn't go over this before, but you can see right here it shows the order in which you're to torque the head. If you didn't have this, a good thing to remember is always start from the center, work your way out. As you can see, this kind of goes in a clockwise orientation as it goes outward until the last bolt is torqued. And that's a pattern you want to follow, and of course in the steps as suggested here on how many foot-pounds you torque it to in each stage. The other thing I wanted to mention was when these cylinder heads are first dropped in place, it's a good idea to make sure they're seated. I use just a plastic dead blow hammer to make sure that that goes down on the dowels evenly and all the way. You certainly wouldn't want to start torquing the head down if it wasn't properly seated all the way. That would cause you some grief. So just a couple tips there, and as you can see, I have painted the aluminum trick flow heads to be my dirty little secret that these look like cast iron stock fuelie heads from the 60s. One last thing I wanted to say or mention about installing these heads is when you're using the head studs instead of head bolts, as you're running those things in, of course you're going to have your threads already chased well before you start this part of the assembly, back when it's bare block. But pay attention to how far the studs are into the block. If you see one that looks like it's sticking up a little bit above the rest of them before you even start putting the nuts on, go ahead and disassemble it. Make sure you've corrected whatever's going on, keeping that thing from going in all the way, and that'll save you a little headache down the line. I don't think I covered this during the build, but this motor came with originally a canister type filter, and if you want to put a spin-on filter, there's a couple options. This is the best option if you don't have the original parts for the canister type filter. If you still have those original parts, GM makes a really nice adapter for a spin-on. I didn't have that with this one. So this one's from Permacool. It has an O-ring around the outside perimeter underneath this, and then in the center, kind of where you see that bolt pattern right there, is a flat gasket that goes on the block. I've seen some that have some sort of felt insert thing. They're pretty junky. This one actually had one on it when I pulled it apart, and it had come apart in pieces. I don't even think the oil was being filtered. We've got this non-bypass Wix racing filter with anti-drain back. So this is a good piece right here, but you aren't going to get any bypass, so you do need to make sure your filters never had the opportunity to get clogged from going way too past you know, a good interval for a high performance engine. So here's something interesting. I was going to run my hydraulic flat tappet lifter with the cam set up so I could check the push rod length that I need, see how the rocker was coming in contact with the valve stem, and check that pattern. And you know, the spring pressure won't allow that with this hydraulic plunger. It's going to go down. I even tried it with a spring check, a real lightweight spring check in place of the valve spring. So I bought this solid lifter from Comp Cams, and it's 151 thousandths deeper the plunger is. So what I'm going to have to do is use that solid lifter, come up with my push rod length, and subtract that 151 thousandths out. And I'll probably take another 20 out, because that's probably how much preload I'm going to run on this lifter, is about 20 thousandths. And so I have to go from there. Got my adjustable push rod in place now in my lifter, and I went ahead and threw some ink on the valve stem tip so we can get a measurement and see how that wear pattern goes across there after rotating the engine through the full lift cycle. And we'll pull it off, see how it looks. The ink I used wasn't the best for this. I didn't have layout ink. This is just some permanent marker ink, but it did allow that to show up, and it is running right in the center and right about 85 thousandths in the width across that mark. Comp Cams likes to keep it closer to 80, but I'm not going to worry about 5 thousandths difference in that pattern right there. Looks pretty good. So another thing you're going to want to check at this point is looking between the rocker arm and the retainer, and look at that through the full cycle, the whole lift of the valve, just to make sure there's no interference there. Make sure you got plenty of clearance, and then of course check for coil bind at full lift, and make sure you got 60 thousandths plus in there. And if that is the case, then you are in good running order. So another thing you're going to want to check at this point is looking between the rocker arm and the retainer, and look at that through the full cycle, the whole lift of the valve, just to make sure there's no interference there. Make sure you got plenty of clearance, and then of course check for coil bind at full lift, and make sure you got 60 thousandths plus in there, and if that is the case, then you are in good running order. Here I am at full valve lift, and it's 500 lift. I have probably way better than 1/8 of an inch between my coils, so I'm not worried about coil bind. And as you can see from what I showed earlier, at 0 lift up to the full lift, there is plenty of room around the retainer from the rocker arm.
Just in case anybody was wondering, I was definitely not going to put this filter on without pre-filling it. Of course, the motor was upside down when you saw it last, and that wasn't a possibility for me. So, just for those who were curious.
I'm using ARP flywheel bolts, and ARP really doesn't want you using anything other, of course, than thread lock on the threads. But they do want the lubricant that they have for fastener and lubricant just underneath the head of the bolt. So I'm just going to have to go around and do this to each individual one before putting thread lock on the actual threads and running the bolts in and torquing it to 75 foot-pounds.
Just got through installing all the lifters. These were coated with Comp Cam's assembly lube on the face of the lifters, and then the bores I coated with their motor oil and dropped them in. Also on a 327 early model, we're got this little PVC, positive crank ventilation, sorry, PCV breather baffle that had to be installed. And on these lifters, these are their race hydraulic lifters, and you can see the part number there. These they call for 0 to 1/8 inch turn on the preload for these, so there's very little preload on these lifters. And so we're just going to go ahead, and when we get the custom push rod, length push rods come in, get these started going, and set those to 1/8 inch turn past 0. So I'm going to be a rebel and not use the 242 medium strength Loctite on these flywheel bolts. You know, Permatex has come out this thread locker orange. It's a high strength, but it's removable like the blue is, but it has the strength of the red. So I'm going to give this a shot. I've heard good things about it, and I will let you know if it fails me. I bought an aftermarket starter, and they want that pinion gear to have about 35 to 20 thousandths clearance right between the ring gear and the pinion gear in there, and I'm just a hair over 35. I have no shims in here. Of course, the block is nice and clean, so I'm not going to get any tighter than that without machining the starter. I feel pretty comfortable with that setting. You do want to make sure you have about 75% at least of the engagement in the pinion gear on the ring gear, which I have. They say that you can, you know, either pry this gear out against the spring to check it, or just, you know, hook up the solenoid and shoot it out there and do that. I prefer just to take the solenoid off and operate the mechanical part of it, and it's so much easier when you're shimming or running it in and out. And of course, also checking at different points on the flywheel just to make sure. You can see this little mark here, and I've rotated it 120 degrees from this mark, and just going to continue doing that, so make sure that it looks good full circle. Make sure there's no run out or problems where it's running too tight. I got my new Comp Cam Magnum push rods, custom length. These are 80 thousandths thickness wall, chromoly hardened, of course, for running in guide plates. And these are one piece. They're not ones that have the swedged on ends or pressed on. And so these are a pretty nice unit. Not top of the line, but definitely a little bit overkill for this flat tappet hydraulic can. It's only got 300 pounds of open pressure and 120 seated pressure for the valve spring, so these will work out well.
and our maximum red line is going to be about 6,500. The lifters will get some assembly oil dropped on the top of them as I drop the push rods in, and then we'll get the rocker set up. Something I don't think I covered during this build is the importance, of course, is cleanliness. You know, most of us think, hey, you got a new part, it's good to go, slap it in. You never want to do that. Just like these push rods, you know, these were all cleaned in solvent. I sprayed brake clean through the middle of them, blew them out with air, and they even took the time to inspect each one and look inside and make sure it was clean, no obstructions. Same with hardware, whether it be screw-in, you know, studs or guide plates. Any of the hardware that I've used, fasteners for the motor, anything that's going in the engine, basically clean it and solvent and dry it, and make sure it's free of contaminants that you don't want to get in your oiling system. So I've got the first guide plate in place and the first two studs in, but they're not torqued. I'm going to make sure that the alignment looks good. Where the roller tip is going to be sitting on the valve head of the stem, and there is a little slack in those guide plates as they are underneath those screw-in studs, so you want to make sure they're centered to the best of their ability, and then tighten them up and go ahead and torque them. Okay, I just got the studs torqued down to 55 foot-pounds, and all the guide plates are aligned. I bought these rocker arms. They were new old stock and they were kind of dirty, so I cleaned them up with solvent and blew them out with air, and then soaked them overnight in oil. Got these placed on the rocker studs, and I'm going to adjust the valves now. There's a couple of 2 or 3 different ways to do it. Old school would be set it on top dead #1 compression. You can set 8 of the valves, turn it 180 degrees, set the other 8. Another way is just turning it, clocking the motor 8 different times, which this balancer is marked for, which you could do as well. There's a sequence chart that tells you what valves you can adjust after the motor has been turned, each 90-degree increment. The thing I'm going to do is just follow comp cams, can't mess up guide, and we'll go over that just here in a minute, and we'll do it that way. This part of the video is going to be a little difficult because I'm here by myself turning this engine and trying to film this, but that lifter closest to me is the intake valve. Furthest one is exhaust. So comp wants you to turn the motor over in the normal direction of rotation, which I'm doing now. And you're going to see maximum lift. And then when the valve is back down on its way, you just saw it moving back down, that's when you're going to adjust your exhaust valve. And then I'll show you when the intake should be set. Now for setting the intake valve, you're going to turn the motor in the same direction that it normally turns. And as soon as you see the exhaust valve start to rise right there, you can go ahead and set the intake valve. Okay, I'm going to look to get my zero lash first. As you can see, there's some movement in there. I'm just going to turn this adjusting nut a little at a time. A little bit still left. Just right there, I'm hitting zero lash. Just a hair more. So I've got zero lash of vertical movement. I'm going to come in here, turn an 1/8 of a turn, and then lock it down, and that's set. After my last video on valve adjustment, I've finished up getting the motor together. Other than that, intake is not really bolted down, and got all the accessories on it, and started to get it ready for firing up, putting it back in the little hot rod. And I had a problem with finding some valve springs that would be good break-in springs for this flat tappet cam, and just with the recommendations comp cam's making for valve spring pressures, I really couldn't find something suitable without spending a lot more money, and also changing out my retainers and keepers along with all the hassle. So I did come up with just putting a break-in rocker roller on it. It's a 1.3 ratio. Should be a lot less stress on the camshaft during break-in. And that's the route I'm going to go, and then swap these out. Probably put them up for sale right after I use them. Unfortunately, these are about $240 to spend, but get some of that money back out of them when I get done with them and resell them. But I'm anxious to get this thing fired up and get the cam broken in and see how she sounds.
So here's a little T-bucket. The 327 went in. Just a little update. I could not use those 1.3 ratio rockers. Couldn't even get them on there without the push rods interfering with the holes going through the head. It was a big mess, so didn't use those. Also, you notice I took the 2 barrels off and put two 4 barrels on. The 2 barrels ran great, but the idle circuits were just not designed for dual carburetors, and I never could get them to idle below about 1200 RPM. So that became an issue, and we just moved on and got the Quick Fuel Technologies 450 CFM Slayer series, and they worked out really good. So check out this little clip coming up, and you can see what I'm talking about. Video of the build, and we'll see you on the next one. Y'all take care.